Thank you very much. Yeah, I would also like to thank the organizers for inviting me, and it's my pleasure to be here. So I'm going to talk about limit shapes. I have also a lot of pictures, and many of these were not produced by me. So I, let's say, borrowed from the colleagues, their presentations and papers, many of them around here. So I'd like to credit them. So we have seen many of the, well, limit shapes already. So there is a zoo of limit shapes. Here is a random lozenge tiling. Here is a Young tableau limit shape. This is the 6-vertex limit shape with domain boundary condition, but Vadim showed also with the weights when you have some antiferroelectric regime. And then this is a non-intersecting Brownian bridge limit shape emanating from one point source to another. And kind of a unifying approach for them is this variational approach, which when you want to minimize a certain surface tension. So these all can be described. These are all surfaces. There is some height function, and then you have this kind of radial variational problem, just like for minimal surfaces. But of course, this surface tension has some different properties than in this case. It's more singular and degenerate on the boundary, which will result in this formation of these facets. So for me, the motivation of this variational approach is that, well, it's very general, applies for different models and also for general boundary conditions, and also that one would just like to understand what's special about this surface tension, what are the common features. We have seen in Philip's talk some mysterious limit shape bijections, so that should be translated on properties of the surface tension. And even so, in this case, we have learned that even Filippo can tell us what is this interior boundary. So, but maybe we can get some hints through the surface tension, what it should look like. And but in today's talk, I will talk about this kind of free fermionic situations when the surface tension is. So the main difficulty here is that we don't even know we don't know exactly the surface tension. In these cases, we know surface tension, and even if you know the surface tension, of course, to solve a boundary with some boundary value problem is maybe difficult. So in today's talk, I'm going to talk about the boundary conditions, which are kind of a one-sided boundary conditions, in which case you can solve it. It becomes much simpler, and you can solve it very explicitly. And in these two models, and many of this kind of results in one way or another are known, but I would like to revisit them from this point of view of the variational approach, and particularly applying what can be called the tangent plane method. So, which I will come to. It's a different from the usual tangent method, which we have seen in Philip's talk, but it's certainly related in spirit. Okay, so this is of course called the Brownian watermelon. So let's see, for obvious reasons. So let's see, whenever you have a surface tension, you can consider the isoperimetric problem. So you have some volume constraint, and you want to minimize that kind of surface. And then the Wolff construction, taking the Legendre dual of the surface tension itself, solve this kind of automatically. But it's kind of used. Sometimes it's better to work with the surface tension, sometimes with its Legendre dual, or actually, usually it's kind of with both of them at the same time. And in some sense, the Wolff shape comes before the surface tension, because, of course, for a particular model, you have to solve this surface tension, and this Wolff shape itself arises as a kind of the ultimate limit shape of the model. So for the lozenge tiling, this would be the 3D Young diagram limit shape. And you can see many of the features already for this solution: the formation of facets, the transition between in the facet and rough regions and connections to algebraic geometry and so on. Our key property for the surface tension for the dimer model, or more generally for free fermionic models, is that this Hessian determinant is a constant. Well, in the usual normalization, it's a pi squared. So this was shown for the dimer model of Kenyon-Okounkov-Sheffield. This is basically equivalent to the fact that the spectral curve is a Harnack curve. And then, using this connection with the Harnack curves, Kenyon and Okounkov studied this limit shape problem for this kind of polygonal boundary condition, and they were able to, for the losange model, construct a matching inscribed algebraic curve from which you can describe the limit shape. For some other, of course, there is a huge literature on this subject, but I just picked those where you allow polygonal boundary conditions with arbitrary many sizes. There might be more. So there is work by Petrov, Bufetov, Gorin, Bufetov, Knizel for losanges and dominoes, when they can actually also prove the fluctuations. And then we studied this variential problem with Astraladus and Zhong from a little bit different point of view. We know that there is a minimizer, and to try to prove things about the minimizer. And we kind of use more explicitly this property of the Hessian determinant. And of course, we have seen more on dimer limit shapes in Alexei's talk. And one kind of funny feature is, of course, these limit shapes are different between the models, but the frozen boundary, when you project it to the plane and you see these frozen boundaries, these algebraic curves, that they are actually universal, so independent of the particular dimer model. And for that, there is a simple reason that, so there is an Euler-Lagrange equation, and there is some coordinate z, and then you can write this equation in terms of this coordinate, and either as a Beltrami equation or a complex Burgers equation. So let's write it as a complex Burgers equation. And it satisfies this type of equation. So this x derivative divided by y derivative is some gamma of z. And this gamma is, of course, it depends on the particular model. So it will depend on the surface tension, but it's a holomorphic function of z itself. So you could, instead of writing this equation for z, you could write directly for gamma. And then since gamma was holomorphic in z, this is the same as zx over zy. But then you get just gamma sigma of z. And then in this equation, you can forget about the sigma. It's a universal equation, doesn't depend on sigma anymore. So the equation for the complex structure itself is this universal equation for the lozenge tilings. And from this work, I would just like to point out one key ingredient, what was for us. So that why these curves are always algebraic. Of course, you can, if you have your boundary conditions, you can maybe solve them explicitly and find that it's algebraic, but kind of a more robust argument, which works in more generality, is that what you want to do is just like we have seen in Alexei's talk, that you can double up the amoeba to get a Riemann surface. You want to do this with the liquid region also in its intrinsic complex structure. But the issue is that there is, a priori, there is a lack of continuity up to the boundary. It's not easy to prove from the variential problem that it would be, let's say, the gradient would be continuous up to the boundary. It is, in fact, not continuous because, well, at tangency points you have some discontinuities, but it will be continuous in this intrinsic coordinate z. But a priori, and this Da Silva and Sabin did prove this, you can only prove this kind of properness, that as you approach the boundary, this also approaches the boundary of the gradient constraint. So a priori, we only have this kind of properness also for the z coordinate or for the complex structure. But here, this complex Burgers helps because we have, after all, some holomorphicity, and then you can just reflect, and then the properness plus holomorphicity ensures the weak form of holomorphicity, which then upgrades to holomorphicity, and then so you have no issue anymore, and then you get the algebraic curves from this kind of extremal boundary conditions. Now, how to introduce this z coordinate, this complex variable? Well, we know how to do it in the dimers, but there should be a story, let's say, in the 6-vertex model also. So we kind of, partly motivated by that, with Rick, we introduced this in a more general way, so in a more abstract way. So we have a, well, let's say we have some strictly convex surface tension. There is also there is this wave shape, and then we don't know what it is, but anyway, we can use this that this sigma gives us a Riemannian metric, and then we can introduce this as an isothermal coordinate. So in terms of the sigma, one can define this gamma, which would be in the dimer world the analog of the logarithmic Gauss map, and then one has to solve this kind of Beltrami equation to find this complex coordinate z. So now, well, as the slope kind of coordinates can be encoded by this complex variable, and also if you have some liquid region, there is a height function, there is some gradient, then there is some slopes. In the end, it can be encoded by this complex valued function. And then if you rewrite the Euler Lagrange equation in terms of the z, you get, again, this type of equation. Gamma is, in general, of course, now it's, of course, not going to be holomorphic. It's going to be more complicated. And this would be, anyway, the analog of this complex Burgers. And then our kind of motto is to write everything in terms of this z coordinate. So let's see what can we do with this. We can also okay, there is this Hessian determinant was important, so let's call this square root of the Hessian determinant in the usual Euclidean variables, but view it as a function of, after all, this SNT were a function of z, so we can view this function also as a function in terms of this complex z, and let's call this kappa. And then we will have some kappa harmonic functions, so this kind of inhomogeneous Laplacian, satisfying this inhomogeneous Laplacian. Namely, as a function of the z variable, the slope variables S and T are kappa harmonic in the liquid region. And so this ST describes if you think of the tangent plane to the surface, this describes the gradient of the tangent plane. But to find the exact tangent plane, I also have to tell what height. I mean, I can still shift in vertical direction. So I have to specify 3 coefficients for the tangent planes, and this would be the third coefficient. And that's also kappa harmonic in this z. This is exactly the Euler Lagrange equation. Now we have seen that for free fermionic models, this kappa is just constant, so we get harmonic functions. So as a corollary, we see that if you think of the in terms of the tangent plane, so we have a family of planes in R3 where all the coefficients are moving in a harmonic fashion, and then their envelope gives the limit surface. So there is a kind of analogy here with the minimal surfaces. Also in the isothermal coordinate, you can represent them in terms of harmonic functions, but then x and y, and so the projection and then the height will all be harmonic. In our case, it's the Legendre, this kind of Legendre coordinates are harmonic, and because gamma was here holomorphic. In this case, gamma is anti-holomorphic. So, of course, there should be maybe a more direct connection with the Lorentz maximal surface as we have seen in Mariana's talk. So this is the the Arctic circle in the Aztec diamond limit shape for dominoes, and this is this Lorentz maximal surface. And well, in this case, they are exactly the Legendre duals, and so they give the same complex structure. Now, there is a tangent, the usual tangent method due to Colombo and Sportiello, which is similar in spirit, where they introduce this some boundary defect to force in the liquid region to force to appear a tangent line, and then to detect the original Arctic curve in terms of the envelope of this tangent light. So now in our case, we can try to find the full limit surface in terms of these tangent planes. Okay, so let's that in general, this kappa might change with Z. So, like in the 6, we have seen in Hugo's talk this sigma the squared variance of the free field in general would change with the slope. So that should have an effect also in the fluctuations. And the effect is that, so there is this non-trivial complex structure given by Z, which also appears in the dimers, but the new effect is that this GFF should be also governed by this inhomogeneous Laplacian. So, and we have seen in Rick's talk that this does appear for a multinomial dimer in workshop 1. So the intensity here is representing the changing of kappa. Okay, so now let's get to the actual setup of the non-intersecting Brownian bridges. So we have some initial data and particles, ordered, and then we send them to some other terminal location at time. So I will use time, y coordinate for the time. And then as we have more and more particles, and then we assume that the initial data converges quickly to some measure mu naught, and then the terminal one to mu 1. Then one is interested what happens in an intermediate time, and that will be given by some measure which is absolutely continuous with respect to x, given by this kind of variational problem. So this is due to Guionnet and other authors, and we are minimizing over here some pairs, this density and this velocity, such that they satisfy this Euler equation, and this is the minimization problem. And actually, if you pair them up in this way, then they satisfy this complex Burger's equation, and this was maybe one of the early appearances of complex Burgers in limit shapes in matches in work. So okay, so now we want to kind of put it in the same framework as the other limit shape. So let's introduce the height function, which is just that we view these bridges as a level line. So we integrate this density up, and that gives you the height function. And in terms of this height function, then we can ask that rewrite this variational problem. So what is the surface tension?
On the previous slide, nu doesn't have physical meaning, so to say. I mean, rho is the density, but you also have nu in the integrational problem.
Yeah. Well, it's kind of a conjugate, whatever. I don't know the physical. It will be related to so it's some of the the derivative of the height function with respect to time. Yeah, okay, yeah. So the surface tension is, looks not so bad. So this is the form. Again, it's Hessian determinant is constant. And well, let's plot the Legendre dual. So this kind of roof shape. Here we see that maybe this is the kind of the simplest surface tension you can imagine for this kind of free fermionic thing. So there is only a single facet. The amoeba boundary is a parabola, and then you have this macroscopic tableau between. And okay, one can then cook up the z coordinate just by this way. So better to think of it in terms of the inverses. So the s and t will be the imaginary part of z and well, z squared. And then you can also view at this dual variables, the partial derivative of sigma and with respect to s and t, they also are harmonic functions. And then if you mix them up, well, then they become harmonic conjugates. And then that can be used to deduce the complex Berger's equation. So namely, then things cancel here. You have some, you had here this z squared z, you get the complex Berger's equation. But then one can go one step further, as we discussed, and ask that, well, in this case, it should be harmonic, this function. So you get, well, this thing will, these are just harmonic, so we cancel. Here you can, well, write the z derivative for s and t. And then at this point, we use complex Bergers. And then we see that here we have the z bar derivative of the identity, which is 0. So we have the harmonicity for this third coefficient as well. Okay, so now we're going to look at one-sided boundary condition, meaning that we have at time 0, we just have the Dirac S, and then on the other side, we have an arbitrary measure. This can be, solution in this case can be represented by free convolution with a rescaled semicircle distribution. But in terms of the limit surface, this can be solved explicitly in this way that, so we take, now the z will be the u minus the Cauchy transform of the measure. X coordinate is parameterized by this y in this way. So u runs through the upper half plane, and the height function itself is given here. So this is how the surface looks like now in 3 dimensions. Okay, so how the proof goes. So we know that, well, we want to find the limit surface as a harmonic envelope of certain planes. Kind of the issue is that we have to match we have the boundary condition in terms of the x and y coordinates, and we want to find what happens with z on the boundary and the involved harmonic functions. Anyway, but so if you just look for an envelope of such planes, as the first coefficient was s, t, and then the third was c, this will be the equation for the envelope. Let's rewrite it a little bit in this way, and then okay, I was this function c is actually multi-valued in the z variable. So let's introduce a new variable. We think of this as a new variable u, and that will be, in terms of that, everything will be single valued. And then since this was the gamma, this is just a minus z, but we use now z as a function of this u. And then we have this kind of equation. Z is a holomorphic function of u. And now since we have this equation at time 1, we have a very simple relation between this physical coordinate x and kind of the intrinsic coordinate u. They are just equal. And we know what should be the imaginary part of z on this boundary given by mu. So that's why we take the Cauchy transform and the normalization, because of the normalization of infinity, this is what you have to take. And then what is, but you also know on the boundary the Lejeune dual of the C plus T, which is given by this function and taking care of some singularities. So you have to add this kind of term. So indeed, now if we define C plus T in this way, then this U derivative becomes this. So this verifies that this is indeed minus U. And then the solution has the right boundary behavior. And in the end, well, H is given by this formula. We know now what S, when X, Y, S, T, and also what C plus T in terms of U. So there is a similar story for another model, which is the random Young tableau. So here is an illustration for the square diagram. So we have a fixed shape of a diagram, in this case a square, and then we look at a random Young tableau on top of it. So they have to increase, these numbers have to increase in these two directions. And then we have this kind of shape. So X, well, Y will be describe the value of the tableau in a normalized way. So I view this as a time. In this case, this is how the surface would look like in this way. But if you rotate things around, then you see this frozen ellipse. And then it's better to represent the surface actually over that plane. So that's why I chose these coordinates, X and Y. Yeah. Uniform measure, right, yeah. There is a surface tension for this problem also, well, in this case, the S and T lie in this region. Now the surface tension, well, of this form, here was for the Brownian bridges. But in terms of this intrinsic Z coordinate, there is some relation. So again, the imaginary part of Z appears of now the other harmonic function is the argument. And then you have this harmonic conjugates. But, well, the equation for the complex Burger's equation is the gamma itself is exactly the same. The difference is that the imaginary, this imaginary part of Z is in one of the coordinates, and here now it's in the other one of the coordinates. And then you want to have this one, then you basically only have these two choices. So some results about the Young tableau limit shapes. Bian has actually results for when this shape is prescribed by the general profile, but it's a little bit. It's kind of the limit shapes themselves are implicit in terms of free probability. Then Pittel and Romick calculated the square Young tableau limit shape or rectangular one and other variants. Only a few explicit examples. And then recently, Borga, Boutier, Ferrier, and Melio actually solved this for an arbitrary rectangle. So we have a fixed discrete diagram, and this is what you approach in the limit. So the profile is kind of this rectangular profile, and Jakobov gave a talk about this in workshop 2. In terms of this work, this was solved as a family of a one-dimensional variational problem. But if you view this as this genuinely two-dimensional variational problem with this intrinsic C, then one can also solve it for an arbitrary profile. So now, well, the omega is our profile function. Here it's some Lifshitz function describing the shape of the Young diagram in the limit. Then you can take its second derivative. It gives you a sign measure, and then define this g function for the profile. It will be holomorphic in the variable u. This is the g function of Karov. So this tau is, well, quite directly related to the geometry of the profile, of the Euclidean geometry. And then, but there is also another measure, which is a probability measure, that this function is a Cauchy transform of some probability measure called the transition measure. That's more describes its intrinsic geometry from one side, but you can then also look it from the other side, and that's called the co-transition measure. So for that, well, there is also the area of the diagram appearing, and then so the reciprocal of this g is equal to some other appearing some other measure, the co-transition measure, and its Cauchy transform. Okay, and in terms of these functions, so now the z variable will be, again, u will run through the upper half plane. The z variable is now the will be the reciprocal of this g function, and this is the equation just like before. So in terms of that, now x and y again parameterized by u in this way, and then the height function itself is given by this formula. Of course, if you have the proof is similar. Now we have the argument prescribed, so that's why we cook up this g function. And then also on the boundary, you have to consider this one-dimensional Legendre transform. And we know that everything is this function is harmonic also. We know the boundary values and then construct the extension. So some examples. Of course, if you have a rectangular profile, then this g function is very simple. It's a rational function with prescribed poles and zeros. You can consider this kind of triangle shape with arbitrary slope. Then z would create a slit. And then this is how the surfaces look like in 3 dimensions. Okay, we have seen that there was some relation between the surface tangents. Yeah.
Before you go on, so is this g function, does it come from the Coupling formula for the number of standard Young tableaux?
I mean, well, what do you mean that it comes from? So,
I mean, there is a formula which counts the number of standard Young tableaux. So you can imagine that the number of those that reach this shape is something, and then you're trying to optimize for that. But if you didn't have that formula, would you still be able to do that?
Well, yeah, I mean, this is the definition of, here is the definition of the g function. Of course, you need to know the exact form of the surface. So for this, to introduce the g function is you don't need a Hooke's formula. It's here, how you do it. But of course, that this describes the limit shape. You need to know the structure of the surface tangent. In that one, the Hooke length formula doesn't necessarily appear directly either, but more like a kind of a degeneration of the Losange model. But there should be some relation, right? So we have seen that this relation, so that they satisfy the same complex Berger's equation, and there is some relation. So what this means is that there is a kind of duality. So if you consider a diagram and its cotransition measure, and now we view that cotransition measure as your terminal distribution for the Brownian bridges, then at the intermediate time, the particle distribution will be exactly the cotransition measure of the intermediate profile at that time. So there is this kind of duality between these shapes. And there is also a connection to free compression. So in terms of the R transform, one can introduce this free compression with some number alpha smaller than 1. So define this new measure in terms of R transform by putting this alpha inside here. It's related to the free convolution. And Bian, in fact, described the limit shapes of Young-Tableau limit shapes in terms of this free compression. So the transition, this time the transition measures of the contours are given by this free compression. Motivated by minors for random matrices, Shlaktenko, Tao, and Johnston formulated from the variational perspective, so found this surface tension for this process. And we can ask now what is the what's the Hessian determinant this time, for instance. Now it's not going to be constant. It's a pi squared over t to the power 4. But still there is some intrinsic, I mean, you can still introduce this isothermal coordinate, and this time it will be the ratio of the argument of z divided by the imaginary part of z, and t is simply the reciprocal of the imaginary part of z. So it does satisfy this property that its Hessian determinant is, so now you have here the imaginary part of z to the power 4, so it's a harmonic function to the power 4. And this is what we call the trivial potential property, and what the phi vertex model satisfies. In this case, this trivial potential property is actually a bit fake, because so you can use this surface given by this alpha, lambda, and x, but if you view it from a different projection, then the corresponding surface tension will be just I mean, it will be a constant with a constant kappa. So again, these surfaces are envelopes of harmonic planes, and then one can then describe them explicitly, relating to the work of Metcalfe. So one can then ask, okay, we prescribed arbitrary boundary condition, but only on one side. So what if you do two-sided boundary condition? So in the Young-Tableau case, this will be skew shapes, and or more general non-intersecting Brownian bridges. So kind of the analog of this extremal boundary conditions is that we have rectangular boundary, or in the case of the Brownian bridges, only atoms. Now we expect, or one can construct solutions of a family of rational solutions, but then, as usual, also in dimers, now the issue, the matching to the boundary conditions, it becomes a difficult problem. Of course, but some simple ones can be treated. And another special case one could ask is that so-called flat-to-flat geometry. So we have now equispaced particles starting and emanating at some time and arriving at the final time also in this way. So actually it's only important to prescribe this on one side again. So one of the measures is the Lebesgue measure on the unit interval. So this was studied in the work of Grella, Mayumdar, and Scher, and then they found, from the Langevin equation, they deduced a complex, a kind of adapted complex Vertex equation for this situation in a non-standard form, and then they were able to, let's say, solve this in a specific time values like 1/4, 1/2, 1/4, and so on, and describe the particle distribution there. In terms of but one can again think of this as an envelope of planes, and solve it in that way. So now we have an arbitrary measure at time 0, and then at final time we have these things. We do the same well, the same trick as before. And again, at then x is simply will be u at time 0. The problem now, of course, that the two sides are interacting. So now we don't know the location of x a priori. But because of this condition, we know that the slope doesn't change anyway. So in this case, kind of the natural region to choose our parameter u will be a strip between 0 and minus I pi. Here x will be equal to u. And here we don't know, but it doesn't matter that much because we know that the integer part just has to lie on this line. And then we solve the kind of the Cauchy, well, use this boundary problem, have this kind of Cauchy transform adapted to this strip, and then z will be given by this g naught u minus u. In particular, when also this initial distribution is a flat thing, so it's given by the Lebesgue measure, then, well, g naught has an explicit form, and then you can integrate out the surface explicitly, and it's given in terms of some d logarithm functions and so on. Once we have this, one can ask that what is the relation between their complex Burgers equation and then the usual complex Burgers equation. And well, there is a relation, but it's a bit tricky. So they have a function g, which is related with a functional equation to this z in this way. You have to invert this g naught. And then also their equation, so this g satisfies the complex Burgers equation, but not in the xy coordinates, but in this transformed coordinates. And that's how they solve it. So, well, we have seen that this harmonic envelope method, kind of a geometric way, can help to solve these limit shape problems. So I will finish with this. Thank you.